So our first speaker this morning, our keynote speaker, is John Colley, who's a research fellow at the University of Southampton. I know John's spent a long time working in formal verification, so it's an honour to have him as our keynote speaker this morning. John has spent 20 years experience in developing the VDA tools for simulation, test generation, code coverage, and model checking. He is now involved in the ongoing development of verification and validation methods for high consequence systems, both formal and simulation-based in defence, rail, and the semiconductor sectors. The title I have on my paper isn't matching the one on the slide at the moment, but it's okay. So it's model-based safety and security analysis and high consequence systems development. This is a personal favourite of mine, because I strongly believe that our industry will be much more involved in both safety and security in our hardware as we move forward with the type of systems we're going to be developing. Safety and security will become very important, and especially in verification, where we have to demonstrate and prove that our systems will be safe and secure. So I'm going to hand over to John. Take it forward. Thank you.
Anyway, you've seen this slide already, and you probably had a good look at it, and you've seen these headlines, and it's becoming more and more frequent. Humans are slamming into driverless cars and exposing a key flaw. The flaw in what? So the software guys and the hardware guys will say our stuff is working perfectly to specification. The car companies, car manufacturers of these driverless cars say it's human error. It's the human drivers. They don't respond as quickly as a driverless car does. Human drivers don't obey the rules of the road. Well, autonomous cars always obey the rules of the road. So now we have this big problem at who's at fault and how we deal with it. So what's happening here is accidents have happened, and a lot of accidents have happened. And what we're seeing is that the accidents are now being investigated after they've happened. Now, what Nancy Leveson says, and I'll talk a lot about her work, is that you actually need to investigate the accident before it happens. You can't just wait until afterwards and say, oh, yes, we never thought of that, but it's not our fault. So this is one of the key things that we need to look at. So what do we need to do? We're developing high-consequence systems. They've got to be safe. They've got to be secure. But you can't just stop. You can't say, there's a problem, I'm just going to close down for 3 days. I know it happens on the rail sometimes. But we still need to get the job done. So fail-safe, as in the railways, isn't always an option. So safety, security, reliability, enableness are what we need to be able to look at. So we're responsible for delivering software, digital hardware components. But how do we assess the contribution of those components to the overall system safety and security? So that's what I want to talk about. So what we're seeing here is, with these driverless cars, the system is all the cars on the roads and the street furniture and the time of day and the levels of traffic. The system is complex. And what we're seeing is emergent behavior that arises from these contributing factors coming together and causing an accident. Now, it may not be an accident. Of course, it may be malicious. Somebody may have, a developer of the autonomous vehicle may have put something in the code which, under certain circumstances, does something which is legal but causes other cars to crash. So there's a lot to think about. So the first thing I want to talk about, and it's a main theme through the talk, is this notion of emergent behavior. I'm sure you've all heard about it. And this is quite a nice definition from 1997. Emergent behavior is that which cannot be predicted through analysis at any level simpler than of the system as a whole. So this is our problem. We need to think about the system as a whole, but we are actually working down at the component level. So what's happening, obviously this is a very high-profile problem. So what they're trying to do in the US government is obviously concerned about this, and they see that we need to think about this from a systems engineering point of view. So there is a new standard which is being ratified in the process of discussion at the moment, the System Security Engineering Standard. So it's for trustworthy, secure systems. And you'll see that in May 2016, so this is quite new. It's actually worth having a look at, this standard. It's 300 pages. There's an awful lot in it. But there's some summaries of it. I think it's really worthwhile to go and have a look and see what the problems are. But the main useful thing about it is it's coming up with some definitions so we can start talking about safety, security with a common language. Here's some nice quotes. The engineering-driven actions necessary to develop more defensible and survivable systems. So defensible is a security issue. Can we get hacked into? But is it survivable? Under attack or under a big accident, can we continue to do something? Can we continue to function? And here's a second quote. This is very early in the standard. Security, like safety and other system quality properties, is an emergent property of a system. So we have this in the standard, the notion of an emergent property. Going on to more about terminology, we need to be able to talk about safety, security, reliability in a cleaner way. So what the standard comes up with is the notion of trustworthiness. So they define trustworthiness in terms of safety, security, reliability, dependability, performance, resilience, survivability. And then it talks about a wide range of potential adversity in the form of disruptions, that's security, attacks, hazards, and threats. So I think this is quite nice. It gives us something in which we can talk. The second quote then says, effective measures of trustworthiness are meaningful only to the extent that the requirements are sufficient, complete, well-defined, and can be accurately assessed. So the first bit is we know what we're doing, but now we need to have this notion of measurement, of coverage. And this is a problem we generally have to face. We can't just go at this ad hoc. So where do we start? We can't start from scratch. We have to look somewhere to see into industry to see that this is already being done already and how we can build upon it. And so a good place to start is with civil aviation. I don't know if you've seen this book. It's quite interesting, called Black Box Thinking. What the summary of the book is that if you look at the way civil aviation has evolved over the last 30, 40 years, they have a very, very good track record of finding problems, fixing them, and ensuring that civil aviation is reasonably safe. So this is probably a good place to start. So the standardization process for civil aviation looks a bit like this. At the top, there's an overall development and design guidance standard, and then there are guidelines for doing safety assessment. We're going to need to think about security, reliability there as well. And then that comes down into software considerations and design guidance for electronic hardware. So we have standards DO178C for software and DO254 for hardware. So I'm sure most of you are familiar with DO254. I would imagine that this DO254 has been used in the electronics industry as a basis for designing reliable digital hardware for years, for the last 25 years. So what I'd like to do is just briefly go over these standards, and these standards are based down at the component level. This is to do with software, digital hardware as a component, and you're assuming that your safety requirements are already, security requirements have already been done, and this is the process that you would use. So it came in 1992, so it's 25 years or so. And the key thing about it is requirements-based testing with structural coverage. So you all know about structural coverage. You have to have full bidirectional traceability from requirements to the implementation. And then if it's the highest level of safety requirements for an aircraft, then you have to use modified condition decision coverage, MCDC coverage, for certification sign-off. So I've got a quick question. How many of you are using MCDC coverage sign-off in your processes? You're doing coverage? Are you using just statement branch coverage, or are you going down to MCDC?
Sound like expression coverage.
Yeah, the other name for it is focused expression coverage. Yes. Okay. Okay, so 178B has now been updated in December 2011 to 178C, and it takes a very successful standard that's been widely used and introduces, first of all, the notion of model-based development and verification, and I'm going to talk about that. Formal methods, so how you apply formal methods to this well-defined methodology and flow. It also talks about object-oriented technology, which I won't go into today. And the other interesting thing is it clarifies. So I say, what's MCDC? It clarifies that definition in terms of masked MCDC, which is focused expression coverage, which is supported in the majority of the tools. Right, so model-based development, as part of my title, is we want to have a model-based flow. And model-based development in the standard, this is the DO331 supplement to 178C, says you need to use a formal modeling notation, which can be textual or graphical, but it must have formal semantics. So the first thing that this precludes is standard UML, because UML doesn't have formal semantics. So you're going to use a formal system, but it can be graphical, but it must have formal semantics. And it supports a model-based methodology. The methodology doesn't change, it's now model-based. So you refine the high-level requirements. You can then, once you have a model, you can do model-based testing, generate the tests automatically. You can do co-simulation. You have a formal model which is executable, so you can co-simulate that, and you can also do code generation. And this isn't futures or science fiction. This standard actually came from, in practice, the use of this flow through a tool called SCADE. So that SCADE is successfully used in avionics, where it's possible to start with a graphical representation at a high level, refine that down, and actually generate code. So there is generated code running in modern aircraft. So formal methods, obviously you've got to have a formal model, so now we want to do some formal analysis. So what the supplement says is that the output of formal verification tool may be used to replace or augment testing. So it's very, very clear. You have to convince the certification authority that of the validity of your formal verification. If you can do that, you can sign off without having to show the testing. If the certification authority is not convinced, then you have to show, in the case of level A software, full focused expression coverage through testing. So it's very nice. It gives you a way of migrating from a coverage-based approach to gradually introducing formal methods, formal verification into your system, but always you have this notion that you can always have the coverage from testing as well. So it's a combination approach. The better your formal methods get, the less testing you need to do. Right, so I've talked about 178C, and that's 254, so it's the gray box. Those are the life cycle processes of the software or digital hardware. But what I want to talk about now is how does the input come about safety and security from the system life cycle processes. So going back to the original picture, we have this red box in the middle, guidelines and methods for safety assessment. This is the way you decide from the system level what are the safety elements that need to be considered in the software and digital hardware of the components. So again, this has been around a long time. This has been running. This is something that we probably don't see so much in the EDA industry, but it's practical. It has a worked example. It's fairly easy to use, but it is now out of date. It doesn't consider model-based or formal, and it's out of step with the other standards. This is the traditional safety assessment flow. And the nice thing about it is you're starting off with requirements and objectives down to the design. You can see there's another little V model in the design, which is where we're working, and then up to certification. This doesn't change. What happens is it's going to be augmented in two key areas. And the two major threads for the restandardization effort are model-based safety analysis, that's to bring it in line with 178C, and system theoretic safety analysis. So they're already seeing that there is a need to take this type of analysis up to the system level, that there has to be some sound theoretical basis to how the system is analyzed. And so I'll talk about these two aspects. So model-based safety analysis. So we've talked about model-based hardware, software development. We now need to think about how we do the safety analysis. So current safety analysis techniques are well established, but they're subjective, manual, and informal. But you don't take those away. What we do is we now use a model-based approach right at the very top level. And the nice thing about having a model at the analysis, safety and security analysis point is that the system engineers and the safety engineers then have a common model of the system that they can use. So model-based development and verification is already supported by 178C. And if you have a model at the fault level, you can then have a formal fault model. So you can actually already start automating using tools on the safety analysis process. It allows formal reasoning. So that's model-based. Now I want to talk about the system theoretic approach. This comes from a book, Engineering a Safer World, by Nancy Leveson, who I talked about earlier. So system theoretic accident model and processes, STAMP. So it's based on system theory, which has been quite a long time around. And there's a change in emphasis from preventing failures to enforcing behavioral safety constraints. So rather than sitting down and think, how many ways can this all go wrong, thinking of all the ways, scenarios that hazards can happen, that safety vulnerabilities can happen, what you're concerned about is defining and enforcing behavioral safety constraints. And this is the link that we use to formal, because if we have a safety constraint, we can represent that in a formal language, and we can reason about it, we can model check it, or we can do some formal proof on it. So this is a major step. Still considered as component failure, but as we know, software digital hardware is not really a component failure. The probability of failure is not something to consider. So, but you still consider that for the mechanical hydraulic parts. So safety is reformulated as a control problem rather than a reliability problem. So the emphasis is on control. So now we can think, if we're developing a digital hardware or software component that has outputs which is influencing the system as a whole, how can that component, in the way that it controls the system, cause an accident or a vulnerability? Three main concepts. Safety constraints, as I said, which we can now gives us the link into formal. Hierarchical control structures. These control structures are not simple. They tend to be layer upon layer with feedback, so you have to think about that. And process models, which I'll talk about. So here's some nice quotes from Leveson's book. Any controller, human or automated, needs a model of the process being controlled to control it effectively. And accidents occur when the controller's process model does not match the state of the system being controlled and the controller issues unsafe commands. And I think if you look at a lot of these safety accidents, it's to do with what's called mode confusion. Airplane crashes, the pilots think that the plane is in a particular mode, and it isn't, and they actually issue commands which are unsafe. Right, so within a STAMP, there's a very practical way of doing hazard and safety analysis called System Theoretic Process Analysis, STPA. And what its purpose is to identify potential causes of accidents, the scenarios that can lead to losses, and then how you can eliminate or control those hazards. It augments the existing mechanisms, and it uses the causal factors identified in STAMP. So STPA happens in two phases. So the first thing you do is you identify potentially hazardous control actions, and then derive the lower level safety constraints from those control actions. And this is the outputs. These are the control outputs of your software or digital hardware. And then having established that there's a potential for hazard or vulnerability, how do those unsafe control actions occur? So now you move in the second phase into how you architect your system so that you can eliminate or mitigate these unsafe control actions. Okay, I'll just go briefly through an example I actually used at last year's conference. And the presentation is online, so if you want to, it's still on the internet. If you want to go and look at it, I'd advise you to. So let's think about landing gear doors on a civil aircraft. And we can see the high-level requirements for the landing gear doors is that the controller, this is a digital controller, will open the doors when the pilot moves the lever to extend or retract the landing gear. The controller will then close the doors when the landing gear is fully extended or retracted. And then there's a key thing, is the doors must remain open while the landing gear is extending or retracting. So those are the outputs from the controller. This is the process model, and you can see the feedback. So this is a process control loop. The controller has a model of the state of the system. It can issue commands to open and close the door through an actuator to the control process, which is the door subsystem, and there's a sensor that can check whether it's actually closed or not. And there's another process, so we have to consider, rather than considering the human as something that just makes mistakes, the human is actually a process that needs to be considered, and equally with the main controller. So the human operator has a process model in mind of the state of the system. And then we can do a simple, but it's a rigorous analysis. It doesn't take long to work out what the potential hazards are. So if the controller action is to open the door, close the door, you say, what happens if you don't provide, can it cause a hazard? So not providing the open door command, you can't extend the landing gear for landing. But providing it when you shouldn't is not hazardous. Close the door, not providing it when you should is not hazardous, but closing the door when you shouldn't can damage the landing gear. So you go through these scenarios, and from this table, you're able to come up with the safety constraints. So you have the high-level objectives, and you can then define the safety constraints. So the first one, if the landing gear is extending, the door must be locked open. If the landing gear is retracting, it must be locked open. And then there are conditions on operations of the system. You can't issue a closed door command if the landing gear is locked up or locked down. It must only be issued if the landing gear is locked up or locked down. Same with an open door. So what we have is natural language constraints, and now we can move into the formal world. So what I've done is I've taken those 4 safety constraints and I've represented them in language event B, but you could represent these in PSL or SVA. And there's 2 types. So the first one is an invariant of the system. The gear state, the state of the gears, either the gears are locked down or locked up. And if they're not locked up or locked down, then the door state must be open. Now the key thing about that invariant, I mean, it's got to hold for the system in all states, is this is an abstraction. This is an abstract level. So we have an abstract model, and we have an abstract invariant dealing with abstract variables. Interestingly, this is quite a useful way of thinking about things when you're actually trying to verify the actual digital hardware. And Ashish, in his talk this afternoon, will talk about this notion of abstraction, how you can use SVA to represent this type of abstraction and get very efficient formal verification. So the first one is an assertion, SVA assertion. The second is, this is how event B works. It's a series of events. We have an event called close, but there's a guard on the event that says that the door state, that the gear state must be locked down or locked up. Otherwise, you can't close the door. So you could also represent that as SVA, but in this case, it's a modal SVA. If the door state is closing, then the gear state must be locked up or locked down. You can check that. So what we have at a very high level is a extended FSM of the system, abstract FSM, but it gives us this notion of completion already at this stage. So very similar to the idea in one spin where you have a notion of completeness of your verification. This is the complete state machine for the high-level system in terms of 3 variables, the gear state, the door state, and the handle being controlled by the pilot. Each of the arcs on the diagram is an event, and the idle event is to do with time. So already this is a synchronous model. So it can tick. At the moment, there are no timing constraints, but that can be introduced. So you have a model that can form the basis of your verification to ensure that you have completeness of the verification. And also you have enough, you've done sufficient assertions to verify this state machine. It's still complex. There are a lot of paths through this particular thing. So anyway, that's from last year's conference. We're still talking about a relatively low level, even though it's an abstraction. What we need to do is, to get up to the system level, we need to take STPA and do it earlier. So what we have here is some work also happening at MIT, Fleming, and it's quite recent, is you take this analysis that I've just talked about and you lift it right up to the concept stage. So at this stage, you have some requirements. It's from different sources. They're evolving. You don't have a specification. But already you need to think about safety and security issues. It's model-based. You can already start thinking about this formally and writing formal assertions about it. And instead of starting with a detailed specification, you start at the concept of operations. So I'll talk about what concept of operations is. ConOps, user-oriented document that describes characteristics for a proposed asset or system. This is one of the first things that's issued, say from the government. The government will say, we want to do this for transport system or aviation. And already you can start thinking about how you're going to develop the system. Okay, I've talked mainly about safety so far, but it's also been shown that you can use STPA for security. So there's a very nice paper on this, which is referred to. And all you do is you take the same ideas of STPA, how hazards can be handled, and you deal with identifying system hazards and security vulnerabilities. So you do the same thing, the system functional control structure, and now you're identifying unsafe or insecure control actions, and now we need to deal with intentional actions as well. So we augment STPA to consider external threat, inside risks, and intentional actions. So exactly the same way as hazards lead to safety incidents, vulnerabilities lead to security incidents. And we're concerned about actually still getting something done. So there's this notion of mission assurance. So you can think about this in the military domain, but it applies into a lot of domains. Mission assurance is the ability to complete a wide range of missions across a wide range of degradations. And this is the kind of thing we want our systems to do, even if it's automotive. We want it to be able to fail gracefully and still do something if something goes wrong. So this is quite a nice way of thinking about it. So the focus now is on getting something done rather than trying to protect the infrastructure and complete the mission. So you're starting at the top, you're starting at the system level, and you focus on trying to control vulnerability. So as I said earlier, you're thinking about how your software or digital hardware component can control the system that could cause it to go bad. So you're concerned mainly about how do I control that, or if my control isn't right, how can that cause a problem? And it's much easier to think about the vulnerabilities because there are likely to be far fewer vulnerabilities than threats. Yeah, the paper is Communications of the ACM, 2014, Young and Levison. So once you have the notion of controlling the vulnerabilities, you can then think about the threat analysis, which is lower level. And because we're thinking about control, we're not concerned what causes the disruption. So we're not going to sit down and think all the ways it can be disrupted. We're just saying, if it is disrupted in some way, how do we control it? So taking these building blocks together, we can come up with a method for model-based trustworthy analysis. So we have a nice definition of what we want in trustworthiness. We incorporate STPA, STCA at the concept level, and STPA security. It's model-based. It's done at the early concept, but it takes us down to architecture. And then if we take the system theoretic approach, which is in place and it's been widely used, and then we augment the traditional avionics flow, the standards are out there, you can go and read them and follow those flows. So you can then take this analysis, system-level analysis, into software, digital hardware development, verification, validation, acceptance. And the formal languages you can use, we use Event B, PSL, SVA for modeling and formal analysis. I've got a few minutes, so I'd just like to go through a very quick case study. So I've talked about how you do landing gear, which is a low-level thing. How would you apply safety, security concepts to a much higher-level thing? So Next Gen is the new transportation system from the US, the FAA of looking for this to be rolled out by 2025. And what it's about is replacing the notion of having a ground controller talking to the aircraft and replacing this with digital communication. The shift of emphasis is then from clearance-based, which is how it works at the moment. A controller gives you clearance to come in, to trajectory-based. And you start off with the ConOps. And this is very well described in this. So effectively, you get quite a lot of detail, actually, in the ConOps, which has come out from the government to the FAA. So we need to be able to control these trajectories, aircraft operating on different trajectories. And the thing I'd like to highlight is in red, the Datalink. Datalink provides aircraft intent information. So we're going to have a link between the aircraft and the ground, and it's a digital link. And so now we have a notion of what are the safety and security implications on this digital link, and we need to analyze them. Now, you could just sit here and think about all the possible ways it could go wrong. Somebody who's developing the link could plant nasty code in there. It could be the data could be intercepted because this is traveling between the ground and the air. But what I'd like to do is show you a systematic way of thinking about whether that data link is truly a safety or security issue. So quickly, what a four-dimensional trajectory is. It's 3 dimensions in space and time, represents the current state of the aircraft, but also where it needs to go in case it needs to avoid bad weather. And what we're concerned about is the aircraft conforming to that 4DT? So conformance is the issue we need to look at. And this is basically what a 4DT looks like, and that's come out of the ConOps. So it's a center line, there's some uncertainty, there's a separation zone, and there are waypoints, but the aircraft can have some notion of intent. Okay, so conformance monitoring, and this is it's in a reasonable state of development. It's automated. The conformance monitoring is done on the ground and in the air, and it generates alerts if the aircraft does not meet its agreed performance. So what we want to consider is the trustworthiness of the system, security and reliability, as well as safety. So the hazard vulnerability analysis, this is fairly straightforward, and it's already done, is that the aircraft violate minimum separation, aircraft enters uncontrolled state. This is outside the constraints of the airframe, or the aircraft performs controlled maneuver into the ground. So this is FAA terminology. So there's 3 basic hazards to consider. And from those hazards, vulnerabilities, you can then define, at the highest levels, 3 system-level constraints, which is the aircraft must remain n nauticals apart on miles apart en route, and this varies according to whether you're over the ocean or close to civilization. The aircraft position, velocity must remain within the airframe manufacturer's defined flight envelope. And the aircraft must maintain positive clearance with all terrain, unless it's a runway or a taxiway. Okay, so we've looked at the hazards, the vulnerabilities, we've got the constraints. The next step is to look at the control hierarchy, and we need to think about the feedback loops there. So you have route planning on the ground, you have the pilot who's controlling the aircraft is giving feedback to the pilot, and of course there's the environment in which the aircraft is operating. The STPA control model that I showed for lower level analysis is still used here, it doesn't change. You're still talking about the controller, the control process, the process model, what the algorithms are. And so what you come up with is a composed control function. There's a control function on the ground and the control function in the air. This system is built up mainly of existing facilities. So the ability to pass X, Y, and height data and time data, altitude reports between the aircraft and the ground is already in place. the clearance comes through these data links. So there's a data link from the ground and then a data link to the ground. Data link is an existing capability that's already in aircraft in the US under trial, and it's not been certified to any high level of safety. So the question is, what are the potential hazards? Having this information passing via some digital data link. So we use STPA, as we did before, identify potential hazardous control actions, and derive the safety constraints, and then determine how these can occur. So the first step is, we have a control function, which is the information that's coming from the ground to the aircraft, and then the feedback, the intent of the aircraft going back to the ground. So we have potential unsafe control actions at the trajectory generation point, and potentially unsafe control actions for the piloting function. And it's the hazards violating the safety constraints. So how can these things happen? So there can be errors in the algorithms. The 4DT could be modified by the data link, deliberately or otherwise. Faulty data on a display is a big problem. That's why they're safety critical, the actual display in an aircraft. This could be deliberate or otherwise. And there's latency in communication, and that could be deliberate or otherwise. So how do you deal with these? These are the things that we need to either eliminate or mitigate in the architecture of the system. So we can come down to an architecture, and this is an architecture which will deal with it, is that, and the blocks in red are safety or security reliability critical. On the ground, you have an algorithm, which is safety critical. And then you add a component on the ground, which very simply adds a timestamp to deal with the latency. It does a CRC to deal with any data errors in communication. And then for the security part, it does an encryption. This can pass in through the data link. And then on the other side, you have a safety critical block, which decrypts, does a CRC, and checks the timestamp. By using this architecture, the data link doesn't have to be secure. And so what's nice about this, data link already exists. It's a very, very complex piece of software, the data link. And it's quite possible then to actually come up with this type of architecture and not try to worry about all scenarios anymore. It's a very clear way of analyzing the problem. So finally, I'd just like to then just summarize this model-based flow. So it's driven by concept of operations. System-level constraints are derived from system-level hazard vulnerability analysis. The control hierarchies are defined. Unsafe control actions are identified. The hazards and vulnerabilities are eliminated or mitigated. We're using formal model-based development, and it's integrated with software, digital hardware, development, verification, and validation flow. Thank you very much. Are there any questions?
So yeah, we have about 3 or 4 minutes for questions. If there are any questions from the audience, just put your hand up. Yeah. Just introduce yourself as well.
Hi, I'm Yogesh from Ericsson. The question I have is, in one of the slides you mentioned that the emphasis is moving from preventing failures to enforcing behavioral safety constraints.
Yes.
How can we be absolutely sure we have understood all the safety constraints at the time we're starting off?
All the safety constraints. You have to have this notion of coverage, which effectively relates to my previous talk last year. But the other thing is you don't eliminate the other part still stays in place. So you're still looking for failures. But what you want to be able to do is think about the safety constraints as well from a top-down system level point of view. The issue is you then have to show coverage of these safety constraints with respect to the design. That's why you need formal. That's why you need a model which is a complete, as I showed, which is a state machine of the system, and you have to cover that state machine. And there's a lot of work there, but that's what you need to do. The completeness is the work.
Anything else? Okay. Any more questions? There's one question. I have a question as well, John. Do you introduce yourself, Chris?
Yeah, sure. Chris Edwards for Tech Design Forum. How do you see these methodologies or techniques dealing with the probability. I mean, we're looking at people using sort of neural networks in autonomous vehicles where you can have the problem where the neural network may output a probability of it being a child or a plastic bag crossing the road at 70%, 30%. Do these techniques deal with that kind of thing, or are there modifications that are needed for that?
Yeah. What I've talked about today doesn't deal with probability. I mean, you can still use your existing failure mechanisms to deal with probability. The other way to look at it is can you have a control system which has got this notion of non-determinism in it? This is the problem for the designer. Introducing AI techniques into something that's safety critical is fraught with problems.
So yeah, just my last question. Dealing with DO254, as you say, has been around 25 years, and I haven't seen it change much in 25 years. And the type of systems we're talking about now are probably a lot more complex. And and also our industry, the automotive industry, is probably going to move much, much faster than the avionics industry.
Yeah.
So do you think this is going to scale and also keep up with the
254 has to catch up with 178C, introduce model-based and formal.
Okay.
I think that's what's going to happen, but also you're moving more to using software on the processor.
Yes.
So I think there's, in one way, you're drifting towards 178C anyway.
Okay.
But it does lag behind because it's implicit. You could say I could apply 178C on top of 254, but it is out of date. Yeah.
Okay. Okay. Thank you very much, John. Thank you.